So, as you can see, it's kind of like a triple act between Ariane, myself, and Rachel. So, I'll touch on a couple of thoughts that Ariane had and kind of preview some of the stuff that Rachel has also. So, for me, I'm interested in the structures of galaxies because they tell us something about how the galaxies got to be where they are. The structure reflects exactly how the galaxy grew. If I have a disk, I conserved a lot of angular momentum. If I have a spheroid, it's telling me that I either had a disk and managed to relax it through violent relaxation and the addition of angular momentum with different vectors, or I managed to just accrete material from lots of axes. And also whether something's extended or compact is also very important because it tells you about the degree of dissipation and loss of angular momentum that a body has when it's growing. And so a question I've been interested in for a while is just to understand the extent to which quiescent galaxies have distinctive set of structures compared to their star-forming brethren. It's quite possible that they would have very similar structures if there was, the same set of events and it was just a stochastic, oh sorry guys, you've just lost your gas. That's totally possible. It's also possible that there's a special process that changes both structure and shuts off star formation. And so I'm going to give kind of an observational overview, and this is a slightly more detailed version basically of the one or two slides that Frank had on it this morning. And so I'm going to focus mostly on central galaxies. So those are galaxies that are in the middle of their own dark matter halo. We're not going to talk much about satellites. There has been some work on that, although I actually think cleaning it up might be quite a valuable thing to do with the better diagnostics that we have nowadays.
We'll wash your mouth.
What? Cleaning up satellites?
Sit down in front.
All right. So I wanted to show the Ariane's plot that he was showing a couple minutes ago. I wanted to emphasize two extra things about this. One thing is that this is rest frame G-band, or it's our humanity's best guess of what the rest frame G-band size of a galaxy is. So that's the kind of first time that we tried to look at the size evolution of galaxies in the same rest frame as a function of redshift. And so that's a relatively novel thing to have done. And so it makes it rather more robust and easy to interpret than a number of previous studies. So the two things that I think really bear emphasizing are that at all redshifts, the star-forming galaxies are substantially larger than the quiescent galaxies. And that's particularly the case at higher redshift, although it's true at all redshifts. Right? So that size difference is always there. So some quiescent galaxies are just smaller. The other thing that he didn't show was the density normalization. Right? So this is the number per co-moving cubic furlong of galaxies as a function of their size for the late types. Right? Forget about late types. These are the quiescent galaxies here, the non-star formers. And this just emphasizes that from redshift 3 to the present day, there's been a factor of 10 or more increase in the number of quiescent galaxies. And this is something that's really important to remember. This is the epoch in which also 90% of all the stellar mass in galaxies has formed. But it's not as if... one thing that is interesting is that the formation redshift of the halos that does such a good job of correlating well with the color. So if you take the formation time of the halo, which is generally redshift above 3, and you correlate that and say, okay, that's got something to do with the color, the actual event that causes the emergence of the quiescent galaxy is generally much lower redshift than that formation redshift. That makes it really, this kind of age-matching thing to be really counterintuitive, actually. I think it's a deeply counterintuitive result. All right. So, the population grows continuously, and quenching happens at all epochs, redshift less than 3, and half of that is at redshift less than 1, where it's observationally very accessible. And the central quench galaxies are much more compact than their star-forming friends. So let's look a little bit more in detail at the actual structures of them and how the quiescence tries to, or relates to both the stellar mass of the galaxies and their structures. So this is a plot from a paper I did with a previous version of the candles analysis, where here we have galaxies at a bunch of different redshifts, from redshift 2 all the way down to the present day with Sloan, from 3 times 10 to the 10 through to about 10 to the 11 and a bit, about 3 times 10 to the 11 solar masses. And they're color-coded by star formation activity. Red is quiescent, which means UVJ, quiescent for those of you who like it, plus a lack of 24 micron emission, because there are some 24 micron emitting UVJ galaxies that it's nice to throw in the trash. And so what one can see is that there are quenched galaxies at a very wide range of stellar masses. At all redshifts, all the way from redshift 2 down to the present day. In contrast, if one looks at the Sircich indices, one finds that almost all quenched galaxies have a Sircich index greater than about 2.5 or so, and that result holds true at all redshifts. And so what was, it's not super obvious that you would want to necessarily make quiescent galaxies in the same way at all redshifts. You can imagine there being different ways of doing that as a function of redshift, but the demographics of the population does appear to be reasonably similar from redshift to redshift. They end up smaller, they end up not forming stars, and they end up all with high Sircich indices. And it happens in a wide variety of ranges at all redshifts. There's a couple of almost absolute statements that one can make that it's kind of entertaining to bear in mind. One is that if I don't have a bulge at all, right, so if I'm sitting in the middle of my own halo and I lack a bulge, I appear to not be able to shut off my own star formation. So this is the plot that kind of illustrates that. This is from Sloan Digital Sky Survey, and so it's optical color against stellar mass, and these are galaxies that have Sircich indices less than 1.5, which means a very small or no bulge. And then these are galaxies for comparison that have Sircich index greater than 3, which is galaxies with prominent bulges. And whereas there are plenty of quiescent galaxies in the prominent bulge camp, there are 14 galaxies in this little box up here, and if you look at them, most of them are forming stars and are quite dusty. There's a couple of AGN, and there's one emission line free galaxy, but you look at it and it's a misclass, the Sircich index is wrong. This is the histogram version of this, and so then one sees the number of red centrals, no emission line at all, right? So this is the difference between something that you'd simply say, okay, this is non-star forming based on its colors, and then this is something where you really see no emission line. So a low level of star formation is pretty common in quiescent galaxies. But one sees that, unless I have a big bulge, I tend not to have a non-star forming population. Oh, and I blew that up big, just so you can really hone into the details that there really is, in terms of the no emission line, there's one galaxy and that Sircich index is wrong. Right. So it appears that if I don't have a bulge, I can't shut off my own star formation. The other interesting thing, so Marla Geha and her collaborators wrote this beautiful paper in 2012, also where they looked at the fraction of quenched galaxies, and this I believe was based on both D4000 and emission lines. So if I have a strong 4000 angstrom break and no emission lines, then I can count as being quenched. And so what she did was she went to very isolated galaxies that had to be centrals in their own halo, and she showed that below about 3 times 10 to the 9 solar masses, that there are no quenched central galaxies. Right? So you remember earlier I was pointing out that that quenched galaxies can have a wide range of stellar masses, and it's true. They have a very wide range of stellar mass, but there is a limit. I can't go below about 3 times 10 to the 9 solar masses. And so there is something special about this mass, and having a bulge appears to be very important for correlating with whether I'm quenched or not. Aryan showed this plot before. The important part is, so that this is actually the version that has the different mass spins so that we can make Tim and Frank happy about the relative extra prominence of the oblate distribution. They do dominate the distribution for lower mass galaxies. The main takeaway point here is that most of the, remembering that there are more quiescent galaxies in this mass range than there are up here, the kind of average man on the street quiescent galaxy tends to have oblate axis ratios, so it's something like a spheroid that has an axis ratio of about 1/4, and so it's something pretty flattened like that. It's not a thin disk, right? So you shouldn't think of it as just some dead spiral, because that's a terrible mental image. It has a much bigger bulge, it has a much higher Sursich index, and it has a substantially thicker disk. And so it's not as if there's no morphological transformation that happens when you turn off star formation in a galaxy. But you do leave a rotating, concentrated thing with an axis ratio of 1/4. Until you reach high masses, and then you have triaxial spheroids. So I want to drill a little bit into the details. Sorry about this. It's got all fuzzy too because I overblew it up. Sorry. So I wanted to drill a little bit into the details of, have we made a lot of progress in finding out if there's particular magical parameters that are better at predicting quiescence or better at correlating with quiescence than other parameters. So you'll remember that quiescent galaxies have a very wide range of stellar masses or magnitudes, right? And so that's so that if I wanted a number to predict if something's quiescent or not, you shouldn't give me stellar mass or an absolute magnitude.
Are these all in the same environment, like all centrals, or?
This is Edmund Chung's paper from 2012, and this is redshift 0.5, 5.8, I think, galaxies from Aegis. So it's all galaxies. So basically the redshift, so one reason why, I mean it's hopeless self-advertisement, one reason I showed the 2008 paper that I did is that it's the only one that I know of that actually tries to go after just centrals. All the rest of them go after all galaxies, but then note that most of them are centrals, and so it mostly applies to centrals. Right? The satellite fraction of the population is pretty low. It's not zero though, right? So it'd be great to clean it up, it's just we don't have the data.
The satellite fraction of the low mass quench galaxies is not low.
Oh no, I have the low mass quench galaxies, so below about 10 to the 10, almost everything that's quenched is a satellite. So all these little guys in Virgo, I don't know who is old enough here to actually know and love Virgo and all the little quenched galaxies in it. It's me. But so most of those things that have like really low, so most of the S0s have really low Sursich index, etc. They're just stripped spirals, right? There's no central analog that's quenched of many of the low mass spheroids in Virgo. It's actually kind of entertaining. Because I kind of built my intuition on that, and my intuition was completely wrong. It's a wee bit better now. Okay, so what he's showing is he's showing them the color distribution. So as a function of absolute magnitude, stellar mass. This is inferred velocity dispersion, so m over r. This is surface density, m over r squared, Sursich index, and then a surface density within 1 kiloparsec. And so the gray region encompasses where you go from being mostly blue to mostly red. And so if it's broad, then it's telling you that this is that quiescent galaxies have a broad range of or happen over a broad range of that parameter. If it's narrow, it's telling you that that parameter correlates better with quiescence. And so what you can see is that inferred velocity dispersion, or stellar mass density, or Sursich index, or the density within 1 kiloparsec they all correlate with quiescence, although not particularly perfectly. Right? There's still a broad range over which the transition occurs, and you will notice that there are plenty of high Sursich index things that form stars, right? And things with high densities that manage to form stars, and things with high surface densities within RE, and things with high inferred velocity dispersions that form
This looks a lot
stars.
cleaner though on the bottom right.
Yeah.
A wee bit, yeah. 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 So there are things that are slightly less bad, but it's really not. It's not as if there's a magic bullet. You kind of like one of these plots and be like, yeah, but there isn't. They're just like, oh, okay.
Can I just comment?
Sure, go ahead.
About the Velocity Index, that's still very good corrupt. So if you have a bulge and a disk like a big spiral galaxy, the Scarcity Index will be high. So the Scarcity Index is low, is 1 to 2 for really disky. As you increase the B over T, you get up to 7, 8. So yeah, you are using a lot of data at 5, and then it drops down again. So when you have a double component, you Scarcity
I agree that you could do bulge and disk fits if God had told me that I understand the difference between them.
It's not that you add up stuff there, it's just how you fit the profile.
No, it's absolutely, but it's just that of the parameterizations that we currently have, it's not as if there's something that correlates super duper well with quiescence. Thanks, Greg. All right. There was this interesting work by Van Nockum and collaborators with the 3D HST candle sample, where they tried to estimate the density within 1 kiloparsec in terms of volume, which was a fun trick to try. And in this case also the quiescent fraction correlates with core mass, although again, not particularly perfectly. There's an order of magnitude, or even a little bit more, between where the quiescent fraction is low and where it gets high. So that's also, that's also something that correlates better than stellar mass, but it doesn't correlate perfectly. All right. And then finally I wanted to show some work that we did with, again, the same data set, where Philip Lang, who I guess he still is, at MPE, and so they did the very hard job of taking the images for candles and creating stellar mass maps. And then they've tried to fit those stellar mass maps with bulge disk fits. Now, it sounds like a hard thing to do, and it is. And is it perfect? Definitely not. But it's not an insane thing to try. And so what they did was they asked, well, what's the fraction of quenched galaxies? They then went and binned it by bulge to total ratio, so the blue things are small to no bulges, and then the red things are all bulge-dominated galaxies. And then they show the quiescent fraction as a function of total stellar mass, mass of just the bulge component, or mass of just the disk component. And what they were quite excited about, so it's clearly the quiescent fraction is a strong function of bulge to total, which we knew from before, but they got quite excited about how the bulge mass seems to correlate reasonably well with quiescence. And so this may be another clue, or this might be a slightly better correlation. So I think it's actually there's a lot of work to do to try and understand exactly which parameters correlate better or worse. Let me just so then the best correlations between quiescence and structure are with things like bulge mass, bulge to total ratio, Scarcity to core mass, but there's considerable scatter, and I really want you, thank you, to remember this, that you can find star-forming galaxies with big bulges. Right? You can find, a perfectly respectable elliptical with quite a bit of star formation. They're not super duper common. It's not like, half the population, but they do have.
Will it have a cooling flow, or does it not have to?
Well, you're thinking clusters. I'm thinking even just galaxies.
Okay.
And a cooling flow. I mean, if you're happy to have a cooling flow in a 10 to 12 solar mass envelope, they kind of have to be.
Okay.
Right. All right. So actually, let me show you. I want to show you this. So this plot you've seen before. So Rachel Somerville and Lauren Porter and Joel Premack have developed this simulate model. So they've taken Rachel's model and added bells and whistles and things to have early types made, not just with mergers, etc., but also with disk instabilities. And they've added some updated recipes for AGN feedback, etc. And they also try and track galaxy structures, which is the topic of Rachel's talk. And so Rachel wanted me to show you, or didn't mind if I showed you, this, which is her prediction for, well, I guess wasn't a predict. Did you see the results before?
No, that's okay.
Okay, so it was a prediction. So it's essentially your prediction for what Philip's plot should look like. So I can switch back and forth, because we're good at that. And the part that made everyone actually pretty happy was that this is not terrible. Right? There's all sorts of ways in which models can go remarkably wrong. You know, so the correlation with stellar mass is pretty weak. The correlation with bulge mass is rather stronger, which is, you know, actually kind of it's actually kind of interesting. Let me show you what's under the hood, though. Right? So this is what you'd observe, but then what's actually under the hood is the correlation of the quiescence with thanks, Ray. The correlation of quiescence with both halo mass on one hand, where there's a relatively weak correlation in the context of this particular model, but there's a very strong correlation with the mass of the supermassive black hole that ended up in the galaxy, and the scatter that was in the bulge mass plot, right? Because remember, her model had more scatter, a little bit more scatter than the observations. That scatter is driven by scatter in the bulge mass black hole mass relation, right? But the interesting thing is that it kind of helps us understand or appreciate that, you know, almost a semi-naive interpretation of, well, they happen at a broad range of stellar mass. I guess halo mass isn't the main thing that correlates with quiescence, and there is a correlation with bulge mass that could be quite consistent with the ideas behind AGN feedback. So I will leave it there, and thank you very much for your time.
Time for some questions?
Joel?
Yes, Joel.
Eric, did you or anyone run a principal component analysis to see if the better correlations happen with combined quantities?
Nope. No. So Edmund Chung, I think a couple others, maybe it was Jerome Fang also, they futzed with, I believe Marianne Franks also did this in 2008. What they did was they futzed with taking mass and dividing it by various powers of the radius. And so you can kind of do that and ask what the correlation gets the best. It turns out to be mass divided by radius to the 1.5. Although it doesn't do a particularly much better job than bulge mass, Sursich index, mass within 1 kiloparsec, etc. either. There sadly really is no magic bullet. And the neat thing is that you can just see by looking around in the universe, it's like, oh yeah, there's things that really look like they should be quiescent, and they're not. They're still forming stars. And so there's a lot of stochasticity in the observed universe, and the neat thing about the models is that the models have some of that stochasticity too. I mean, they don't have quiescent fractions of 1 anywhere either. They expect stuff to happen, just like it does in real universe.
Glenn?
So maybe a very naive question, but you're continuously saying at a given redshift, the quiescents are smaller, particularly the size were smaller than the star-forming galaxies.
Yes.
So does this mean that to go from the star-forming into the quiescent, that you automatically have to do this at very early redshift?
No, you can't do it at very early redshift because those galaxies aren't there. They're not quiescent by then. So you have to do it spread over a large range in redshift. Remember, half of all the population comes into place at redshift less than 1. Right? So it means that you have to make the size of the galaxy that you would see in rest frame G smaller. You can do that by kind of getting rid of a star-forming disk. That causes some of it, probably.
But is that sufficient?
We don't know. We don't know.
Wait about 10 minutes.
She knows, I don't. Yeah, but there's also another neat thing that you'll remember. Sorry. You remember how so if you have the star-forming galaxies and then they get bigger towards present day, and then you have the quiescent ones. What happens is, if I'm trying to make a new quiescent galaxy, I can take one that's about here, and I can more or less turn it off. And the point is that the quiescent population evolves somewhat faster. So simply keeping track of, well, I'm not taking these and making them into early types, I'm taking earlier redshift ones, slightly earlier redshift, and turning them into early types. That does a wee bit for you also. So exactly how that works is not.
So it's still unclear which ones will dominate.
I believe that dissipation is going to be an important part of all this, but she'll tell us what her model says, which may or may not correspond to reality.
Jay, did you say?
Just a quick question.
Which is, what about timing? I mean, with AGM feedback, you might expect it to be early, right, in terms of very powerful feedback. That's when you have the very high luminosities, the very fast winds out of quasars. Yet at the same time, you assemble half the mass later. So are you seeing wider impact around the environment of what is going to be the seed of a very massive galaxy that's going to become more extended? Or do you think it could be just that you grow a very dense galaxy that's able to eat everything in sight? In terms of being dense, makes you certainly a nice candidate, dense and massive.
There may
looks like there's a timing difference.
Yeah, so there may be a slight misconception going on here. So the AGN, so the star formation history of the universe peaks more or less at redshift 1 to 2.
Right.
It's not like 2 or 3 or 4 or whatever. It's really about 1 to 2.
Right.
The AGN luminosity function of the universe also does that if you go down to Seyfert luminosities.
Right.
And so I think what it's telling you is that a giant big quasar going boof, right in the middle of every single early type that's formed, that ain't happening. But I think that that a more moderate luminosity event is quite consistent being part of every event. I'm not saying that's what's happening. I'm just saying that that a big quasar I don't think is going to be happening in the middle of every one of these events.
But you do have to grow the, you do have to proportionally grow the black hole, even though you're growing the outer envelope by 50% at the late time, which is a trick, right?
So it's easy to get screwed up with different mass ranges and stuff. So what the very biggest early types is doing is quite different from what we think is happening to the somewhat smaller ones. And there's a range of behaviors for both. So I actually think it's a little bit more complicated than that. Sorry.
I think I want to stop there so we have enough time for discussion. Let's thank Eric again.